All right, so chapter 14 gets real interesting here and very useful when we know that we have a, a situation where we need to find changes in velocity and we don't have any other applied forces other than things that could be classified as potential or kinetic energies. And maybe you've done this before. It's whenever we just say, okay, now let's just make it kinetic and potential, and one converts into the other, right? So a classic situation could be pulling back on an elastic band, right? As that potential energy is released, it turns into kinetic energy, right? Or another example could be a roller coaster, right? It's at some given height, and as it loses that height, its potential energy from being higher relative to these other points is converted into kinetic energy as it gets faster, right? And then as it goes around loops and things like that, it loses kinetic energy as it gets higher and converts back into potential energy, right? So we're able to very fluidly totally bypass accelerations and even work that we had to do in the last section because we can classify it all as kinetic or potential, right? So we're going to introduce this potential energy due to gravity and also due to other types with like spring energy later. But due to gravity, all we care about is what's its height relative to some other point, right? So if we're saying this is the datum, that's ground zero, right? If you're above that point, you have positive weight times change in height y. If you're below ground zero, then you have a negative weight times change in height y, right? That would be your total potential energy. If you're even with it, then you have no relative height. And so you'd have zero potential energy. And you'll notice I'm saying relative height because there's no point where you just have potential energy. It's always relative to some other whatever you call ground zero. And that's what this datum is. And you always get to pick what that is, right? If it makes sense for your problem to say the bottom part of our roller coaster is ground zero, then call everything positive above that, right? If it makes sense for point A here to be the ground zero, call that your datum. And now everything below that has negative potential energy, right? It comes out in the math, but you get to decide what makes it easier for you to keep track of what is the relative datum for everything to be measured from, right? So if it's you set what that is. Above is positive, below is negative, right? It's all relative when we're talking about potential energy due to gravity. Now, potential energy for a spring, again, we've got 1/2 ks squared, but this time instead of saying we're having work done by a spring, we're saying it's potential energy stored up in a spring, right? So that's different than the spring like pushing at a force times a distance, right? We still have the 1/2 ks squared because as the s changes, so does the force, right? So we've still got an integral that happened there to give us 1/2 ks squared, but we could have like an initial pent up energy as it's compressed or maybe stretched, right? That would be our initial kinetic energy, or not kinetic, potential energy in the spring. And then after it's released, either it goes to zero or it could be now compressed, or maybe it's still stretched a little bit, right? And that would be our new potential energy at the end of the process. So we handle it a little differently as a potential energy rather than as a work now. But it's still got similar equation for calculating it. It's just going to end up on two sides of the equation if it has potential energies still stored in it at state one and state two. And we usually give this E for elastic. And notice we've got V now as our potential energy, uh, what we'll plug into our equations for our variable there. Okay, so potential energy, because it's 1/2 ks squared, you can't put any distance in there that's going to make this a negative. So that's always going to be positive, which is interesting. But if you think about it, now it is the case where this is always going to be positive, right? If you stretch out a spring, could it go further stretched when you release it? No, so it's going to be positive potential energy. It's going to shoot at the same direction as the velocity, right? Or if you compress it, right? Now when you release it, it's going to push the same direction as the motion as well. So the kinetic energy and the potential spring energy are always going to be positive there. Okay. So putting this all together, we're going to come up with the idea of conservation of energy, where we're essentially saying as the particle moves, right, and think of our roller coaster, right? As it goes up and down, we're either converting the potential into kinetic or we're converting that kinetic back into potential as we go back uphill, right? So the potential plus the kinetic that we start with at the top has to equal the potential plus the kinetic that we end with at the bottom or whatever other state we end up at, right? Everything is just converting. We can't lose any of that energy anywhere because of the conservation of energy, the second law of thermodynamics, right? Which, if we write it for a conservation of energy with kinetic and potential energies, ends up looking like this, right? The initial kinetic energy plus the initial potential energy, all of that added together has to equal the final sum of the kinetic and potential energies. It is constant. There's no losses there, or at least nothing disappears energy wise. If it did not equal, then there would have to be some friction loss or some other form of losses happening there, heat losses maybe. Okay. So T1 is the kinetic energy, V1 is potential energy, same for T2, V2. And remember from last time, we've got 1/2 mv squared for our kinetic energies. So with that, we've got everything we need to try this out and do some really pretty quick problems now that we have narrowed it down to just potential and kinetic energies.